Hello, thank you for joining us today and joining us for Delta's continuing webinar series. Today we're going to go over RMC PLC communications. Communications has been a very important part of the RMC motion controller family for many years, and the RMCs support a lot of popular industrial communications protocols. Just a few quick reminders. If you've missed any of our past webinars, we've recorded everything. They are available, recordings are available linked from our website. Also, during the webinar, if you have questions, you can enter them in the chat box. We're monitoring those and we'll try to answer those as quickly and as we possibly can. This morning's presenter is Jacob Paso. Jacob is the development manager, product development manager here at Delta, and he's very, very active with support. There's a good chance that if you've called in, you've probably talked to Jacob. And so with that, I'll let him get started.
Thank you, AJ. I would like to remind everybody first that you can enter questions in the chat window, as AJ said, and we'll try to answer those as we go on. So welcome to our webinar about using PLCs with RMCs. We hope to give you a lot of good information that will be helpful in your own projects. Using a PLC and a motion controller and a motion axis is what our customers typically do. It's a very good combination. The RMC motion controller can be standalone in simple applications, but we have to say that the RMC has great motion control features and the PLC has great machine control features, and the combination works very well. First, a little bit about why a hydraulic motion controller to begin with instead of a PLC, because some PLCs say they can do motion. Generally, a motion controller has more motion features than a PLC. There's a few PLCs with pretty serious motion controllers, but for the most part, we're going to have a lot more motion features in a dedicated motion controller. Specifically for hydraulics, a hydraulic motion controller is going to have more features for hydraulics than a PLC is going to have. And we consistently hear our customers say that our motion controller has a lot better troubleshooting capability. One major item is doing position and force control of the same actuator is nearly impossible with a PLC. It's happened that our sales guys have told customers who want to do it that says, when you're done trying, we'll still be here for you. And a few weeks later, after they're done trying, we were still there for them. And it's much easier with the RMC than it is with the PLC. And if you use a hydraulic motion controller, you can usually get away with a smaller PLC because you're offloading a lot of the real heavy-duty calculation to the motion controller. Now, I mentioned hydraulics. We, of course, do electric mechanical actuators as well. So a lot of the supplies for that. We had a customer once who wanted to use a PLC that had come out with some hydraulic features, and they tried it out, and after a while they decided they wanted to use our motion controller instead, and we asked them what the difference was, and all they said was there is no comparison. That wasn't real helpful for us to get detailed comparison, but it is somewhat telling. So enough of this kind of blatant advertising. Today we're going to talk about communication between a and the AJ, was I muted at all? I got a message here about being unmuted. Hopefully you guys didn't miss anything there. We're going to talk about communication between a PLC and an RMC motion controller, and that has to do with communicating back and forth with data. It's pretty simple. It's just reads and writes. That's all it comes down to. So nothing more complicated than that, really. We can read and write all kinds of things. We can read status from the RMC, write parameters, send commands, read-write variables, read plot data, send curves, and so on. All of that amounts to a whole lot of data, especially the plot data. You can get lots and lots of data from the RMC. Now, communications and data, that is a foundation of big data. That's the foundation of Industry 4.0, digitalization, industrial Internet of Things, and so on. The motion controller has always been a support for these types of things. So if you're looking to develop your machines in this direction, a motion controller is a very important part of that. The RMC communicates with many PLCs. We have a few pictures here. This is a list of some of the PLCs we communicate, and we also show here the projects and instructions that we have available for these various PLCs. Allen-Bradley, Siemens, Mitsubishi, we're actually an alliance partner with the Mitsubishi, so we have some good stuff there. Schneider Electric, Automation Direct, Beckhoff, Omron. I noticed we actually do have some examples for GE, but they're a little bit old. We're working on an example for ABB, and of course there's more PLCs we communicate with as well. If you have a question about what RMC or what PLC the RMC can communicate with, or need help with that, we do have instructions and example projects. As I mentioned, you can find those in the RMC tools help. Here's a picture of the help topic using Allen-Bradley controllers via message block. We have help topics on other ones. Let me open up real quickly a little bit of our help so you can see the detail that we actually have. So if I go in help topics and maybe I look up the Siemens PLC, we'll choose using that via Profinet. Here we have a topic. If you scroll down, you see that we have full-fledged examples of all the dialogues and screens that you'll be seeing to set it up inside the PLC. And then at the end, we generally have a little bit of information about using the communications. So very good, complete examples on a lot of the PLCs that we listed here. In addition, on our website, we have a downloads page. Let's go look at that. So if we go to the downloads here on Delta's website at deltamotion.com, we have an example section. We can click PLCs, and we see that we have Allen-Bradley, Mitsubishi, Omron, Siemens, Automation Direct, GE. We have Wonderware, not really a PLC, kind of a soft PLC, I guess. But a lot of these contain example projects that you can look at and documents that give instructions how to use it. We also on our website have some videos available. We have a few of the videos. Let's see if we go to education, video tutorials, and scroll down here in the how-to, I guess under communications. We have video on how to set up the Allen-Bradley PLC with RMC. We have video on the Siemens. I'm not sure how complete that is. And we're working on making more videos also. And if that isn't enough, you can always contact us at technical support. We may have some examples kind of hidden that aren't necessarily quality enough to publish, or we may be happy to help make an example for you, whichever PLC you're using. The RMCs support a lot of communication protocols. In general, the RMC 200, 150, 75 support Ethernet IP. Of course, it's Allen-Bradley centric and a lot of other controllers, and Profinet. Mostly Siemens, but other controllers as well, and Modbus TCP. Between these three, we're covering most of the PLCs that exist. We also support CSP, that's generally Allen-Bradley, like Micrologix, FINS UDP, an older protocol for Omron. Procedure exists for some older Mitsubishi PLCs, and Delta Motion Control Protocol called DMCP, that's our own protocol that we made. It's a very simple one. We actually use that in the guts for the Mitsubishi. We also use it for our embedded C example. Not a PLC, of course, but it's usable there. We also, on some of the controllers, support serial, which is Modbus RTU or DF1 protocols, and on some of them support Profibus. Our newer RMC 200 does not support serial or Profibus because these protocols methods are getting rather old. The world is going to Ethernet. A very important thing for the communications is that the RMC is a slave only. The PLC must be the master. So the PLC must be the one initiating the communications, and the RMC is only listening to it and responding to it. Now there's a lot of terminology that has been invented just to confuse this matter, but master slave is equivalent to client server, scanner adapter, controller device, originator target, active passive, and there's even some other ones just to confuse the issue. But the main point is that the PLC must be able to initiate the communications to the RMC. There's some PLCs that, they may support some of the protocols RMC does, but they're only a slave and that won't work together with RMC. But generally we can communicate with every PLC out there. Occasionally we may need an adapter for some obscure PLC. When we're communicating with the RMC, you need to keep in mind the data types that the RMC allows for communications, and it's 32-bit registers only. And generally it's the real, these are the floating point values, 32-bit IEEE format, double integer, so like an integer such as this, and then a double word, which is a string of bits often represented in hexadecimal format as I list here. And so the key thing here is that the RMC does not support individual Booleans. Now protocols like DF1, the Allen-Bradley DF1 and Modbus, they do support Booleans in the protocol, but the RMC does not support that part of it. We hope to do that in the future. But there are some protocols that don't support individual Booleans, like the Cyclic IO in Ethernet IP or Profinet. So typically our customers are easily able to send bits back and forth just inside of like a D word. Today, we are going to talk about explicit communication that requires an instruction for each read and write. So typically in your ladder logic, you have an instruction every time you want to write to the RMC or read from the RMC. And then we're going to talk about implicit or cyclic communication, where we set it up ahead of time and then it just happens automatically without any instruction in the ladder logic in the PLC. Of course, we do need ladder logic to handle the data, but the communication itself doesn't need anything. So first, the PLCs and PCs, they can read and write RMC data with specific read-write events. So like in a specific instruction can read data from the RMC, maybe axis 0, you want to read actual position, velocity, accel, and you get that in the PLC, or you read from axis 1, or you read from some variables, or you write to some variables. Each one of those from the PLC with a specific instruction you can do. And of course, when we do this, one of the first questions that come up is, what is the address? So to find the address of the item in the RMC, we can use the address maps. So if we look inside the RMC tools, if we look in the project here, this is a controller I'm connected to, we have the address maps. I double click the address maps and we'll talk about the Indirect Data Map a little bit later. We have address maps for each protocol. So each protocol can access all the registers in the RMC, or at least most of them. And we list here the addresses and the registers inside the RMC. So if I want to read a variable, I can see here that we have the variables. I expand that section and click here. This is address 401537. Now with Modbus, the 32-bit register reading is always prefixed with 4, so you just have to remember 1537, that's variable 0. Or if you want to send a command, the command area is 0, starts with 1025, and so on. We can find the addresses. FINS is very similar to Modbus. We'll go back to Modbus. We notice it's what we call a flat address map, just numbers that keep increasing. FINS is similar. We have the similar areas like variables or axis status, and we can find the address. With DF1, we support the F file type. F is generally for floats. We kind of cheat a little bit on this because we have like axis status registers where you have the status bits. That's actually a D word. You can read it as an F file, but then in your PLC, you'll probably have to use a COP instruction to convert it to like an L file, a 32-bit integer. But the address, you can actually address it as an L as well in the RMC directly, either L or F. And you see this is a 2-level. So for each section, we have a number. We call it the file, like 789, and then the element within there. So if we scroll down a little bit, we find the variables. So that's under file F56, element 0 for variable 0, and so on. We have Profinet data records. That's specific to Profinet. Profinet can be cyclic, but the data records are non-cyclic, and we find the address there. The IC is the internal addresses that the RMC uses. The Delta Motion Control Protocol also uses these numbers, and you'll notice these numbers are actually probably similar to DF1. We see this is the RMC 150. If I go to the 200, the address map there, so this is for 200 address map. If I look at Modbus, I don't have so much because RMC 200 has more data than can fit inside the Modbus address map. So we give you some of the most important things, and then you can add your addresses yourself. So let's say I want to start at 430,000. looks like it needs to be in a different range. That was 30,000, and must begin with an odd number, 30,001. And we'll do maybe 100 registers, and we'll assign that maybe to the plots. So I go look for the plots, plot 0. We'll do the static plot upload area, sample set 0 right there. So now I see I've defined the Modbus map address here for reading 100 items of plot 0. So that was an RMC 200 that you have to set up the Modbus address map, or the FINS address map, or the DF1 address map. So that's how you find addresses. We also have other places addresses are displayed, like in the Access Tools. If you right-click the red column, choose Address Format, Modbus, it will show you the addresses. This is a 200 that we haven't assigned these for, but if I go back to the 150 where they are assigned in the Access Tools, we see that right here. This is a Modbus address for Access 0. And then if I click Access 1, we see that it changes. Access 2, it changes. So there are a few places you can see the addresses, but you can see all of them in the address maps. I have hooked up to our computer a PLC. This happens to be an Automation Direct Productivity 1000. No particular reason I chose that one. I have to choose something, and I just happen to have it available. Software is free, I believe. And we have it hooked up to an RMC75E motion controller with an IP address of 192.168.1.85. And we will be using that as we are communicating. So let's go look at a sample read and write in that. So here's the software. You see we are online with the PLC, and I have a simple program here where we are reading from several different locations in the RMC. You see I have a bit that turns on where we can do these reads. We'll do a Modbus read, and if I double click in there, I can see how it's set up. There's a lot of settings here, but the important ones are the IP address, telling it what ARMS or what device to read or write from. I have a structure here. There's just a tag name internally in the PLC. It's saving items to. This PLC is actually kind of cool. It has an automatic polling option. So I'm choosing every 100 milliseconds to rerun the read. So I don't have to do any other logic to make sure it keeps happening. And here's the address of the item I'm reading in the PLC, 4113. So if we go to RMC Tools and we look at the Modbus address 4113, actually that was RMC 200, we went to 150 right there, 4113. See if we can go find that. So that would be right here, 4113. That's the Access 0 actual position that it's reading. And it's putting it then in this array in the PLC, Access Pos 1. That's an array. It looks like it's just putting in the first item. There's a few other settings here with Modbus. Modbus 16-bit protocol doesn't really define the 32-bit. So sometimes you have to swap the data. And then Modbus can be 0-based or 1-based. It's supposed to be 1-based, but some manufacturers make it 0-based. So usually they give you the option of choosing that. So we would add this with like 4112 if it was 0-based. But this is the settings. We're basically reading the Access 0 actual position and putting in that tag. And then we have another read that reads this item here, 4625. That's actually the Access 1 actual position. And we're putting it into Access Pos 2. And then we have a third Modbus read. That's putting it in another array here. That's Access 2 position, I believe. And then a fourth one. We're reading Access 3 actual position, I believe that is. So we're reading from several different locations here. So therefore, we're doing multiple different reads. And if I set this bit, do reads, let's go down here. And on the reads, we'll, let's see, we'll go send that down. We'll set the do reads, turn that on. So it's on, And we see down here in the data view that we have values of 15 and then 14.995 on these axes. Let's see in RMC tools if that's what we have. Sure enough, we have 15 and 14.99. So if I send a command in RMC tools to move to 1, we'll go to slow disk speed 0.5, click send. We see that's moving, the position is changing. We go back here, we see that that position is changing. So we can tell that we are communicating continuously with the RMC, reading that data and getting that data into the PLC. And of course, then we can do whatever we want with that data. We can also do a write. Let's see if I'll go turn off the reading here. We'll go to write simple. And here I want to show first that we're writing a D word. So I'm writing to the RMC again here, and we are choosing to write data from this tag called write data hex. And I'm using hex for hexadecimal that I want to display it in hexadecimal format. It helps troubleshoot the communication. And we're writing it to 1537, which if we go back here to the address maps, we can see that 1537 is, let's see, there, 1537 is variable 0 that we're writing to. So it's writing to variable 0, that value, write data hex. And if we look at this write, we see write data hex here. We're viewing it as hex, so we have this value here, 1, 2, 3, 4, 5, 6, 7, 8 in hexadecimal that we're writing. And looks like it's already applied in the PLC. And if we then set the write data, the do write hex bit, that should do one write, I believe. So we'll send that down. And let's go see in the RMC if anything happened. We go to the programming, variable table, monitor tab. We see that 1, 2, 3, 4, 5, 6, 7, 8 was actually written to variable 0. And we can change that to 0 here, download that, and run that again just to show that we actually did it right. So I'll turn this off, apply it, turn it on, apply it. So now it should go. And we go back here and we see that it happened. Now, if you have problems with communication, you can go to the event log. So we'll double click the event log, tells me when a connection is open and closed. But if I go to settings and choose communications and Ethernet, I can click all application transactions, click OK. Now that will tell me every time I get a write. So let's go try that again. We'll turn this off and then we'll turn it on. So we'll actually trigger the write again. And let's go see in the event log, it says Modbus request received, function, write multiple registers, tells me the address it wrote to and the length of it. It doesn't show me the data, but it shows me all the detail about it. Really good for troubleshooting. I want to mention, especially with Modbus, the reason I do this with a D word is because sometimes Modbus, you might get offset by 0 or 1, so half the word might come in here and half the word might come in the other, or the word might be mixed up. And if I do hexadecimal, it will tell me exactly what the order is of that data, if it's mixed up or if it's offset. And then I can go back in my PLC, in my Modbus settings, and I can adjust whatever settings I need to. So really good troubleshooting. But that's just the hexadecimal. We'll go try a regular write here. We'll see what that is. We're writing to 1539, so that's variable 1. Remember, we're 1537, and being it's a 16-bit protocol, we have to increment by 2 to write to the next 32-bit data, and that's writing from write data 1 as well. So if we put in write data, we'll go write 1000.23 and we'll apply that to the PLC, and then we'll set the do write 100,023. Let's see if that showed up. Sure enough, it showed up. So we can see that we can write and we can read. Now, we have seen that we've done a lot of reads and writes, and that's actually rather inefficient. To do a lot of reads and writes, but you have one piece of data here, one piece of data there, one there. You can either write the whole RMC and pick out a few items, or do multiple reads and writes. It's kind of wasteful either way. So what we do is we gather the data into one place in the RMC. Then you can read from just that area, and we call it the Indirect Data Map. So you might put the actual position from axis 0 in there, actual velocity, whatever, and then from axis 1 you put some things, and then from the PLC you do one read and you get all those items. And similarly, you can do it on the writes. From the PLC you can do one write, you can write to multiple different things here, and those will get spread out into the RMC. It does not eat up any significant extra processing time in the RMC, and this is the standard way we use for PLC communications to make it more efficient. So if we look at the RMC again, go to the address maps, this is where the indirect data map is. So we may want to read, say, axis 0 positions, and we'll map them to right here, and then the PLC will be able to read from here. Notice the reg number column gives us the address of it. So we see it's in Modbus. So the Modbus address here is 1, of course, prefixed by that 400000, whatever. So we'll go map them to axis 0 data actual position. And I can browse for the others, but I'm going to be lazy. I'm going to click this duplicate for axes. So once I have something in there, I'm going to duplicate that for multiple axes by clicking here. Click select all, click OK, and bang, it gave me those for the other axes. Really quick and easy. If I have 20 axes in my controller, this is a really, really nice feature to have. So we'll click OK, and let's see, let's add the axis 0 actual status as well. So we'll go axis 0 status bits, and we'll add it for the other axes too. Select all, OK. Okay, so now they're in there. Now, I can actually mix up the order if I want. So I could go like this. I could go here. I do axis 0, status bits, actual position, and now duplicate this for all the axes. Select all, OK. So now they're duplicated, and now they would be in here. But I'm actually not going to use this now, so I'll delete it, but I could do that. Yellow, of course, means there's a difference between the project and the controller, so we need to download to the controller to apply it to the controller. So now we know the controller is here. So now the PLC, it can read from Modbus address 1 and read all these registers and get all these registers right with one read instead of having to do multiple reads. So let's go see how that looks. I have a program here called Read Consolidated. Let's make sure we have other bits here turned off. I don't want them on at the same time. So Read Consolidated, we're doing a Modbus read, and we see down here the address is 1, and then of course the prefix 4, whatever. And that's reading from the indirect data map. I set this to automatic polling every 300 milliseconds, so the PLC is always getting the data. Normally I do it faster, but I want to do a little bit slower here so we have time to see things. And we're putting that data into an array of 8 items and into these tags, axis 0 position and status bits. Modbus is really nice because it doesn't care about data type. So I can stick in whatever data type I want. If I was using the Allen-Bradley CSP, the DF1 style addressing, it does care about data types. It gets a little bit annoying, but you can always later copy them into the proper data type. So we're doing Modbus function code read holding registers, what we use, and we're putting in to these tags. So click OK, and we will set the bit. Let's see, which bit do we have? Do IDM read right there. Set that, so that should, am I not monitoring this? Okay, looks like I need to apply something to the controller. Wait for it to apply. And now we can monitor. Okay, so we're doing the indirect data map read from this, and we should see that the actual position is getting values, and the status bits are getting values as well. We see hexadecimal value 4002241. If we look in the RMC, the access tools, we can see the status bits have the same value. And let's send a command and change things just to make sure we're actually changing things in the PLC. Here we see that the position is indeed changing down there. And notice the status bit's a little bit different, 2800. While it's moving, once it gets into position, it'll probably change back. So we see that's happening. We can also see in the event log for troubleshooting, we see all these Modbus requests received, and it's happening quite frequently, just like we commanded it to. So the indirect data map is typically how you would read data from the RMC for efficiency. And we see it reached 20 and the status bits came back. One special item is sending commands. So you see a typical command would be a move absolute with some parameters. Each command in the RMC has a number like 20, move absolute is 20, and like move relative would be 21, stop would be 6. That's how the RMC knows what command you're sending it. You send that plus the parameters. So this command number, you send that with these parameters to the RMC, to the command area. This would be axis 0 command area, and then we would have axis 1 command area if you want to send to axis 1. And these are just there's just a place in RMC with an address that you can write to like anything else. So let's go see what that looks like inside the PLC. So we have a write a simple command. In the Modbus write, we are writing to 1025, and if we go to RMC tools and look up the address map for Modbus, we see that 1025 is the axis 0 command area. If we were going to write to axis 1, we would write to 1045 instead of 1025. We're writing to 1025, so we need to write the command number followed with parameters. And we only have to write as many parameters as the command has. So here we're writing, I think it'll be a move absolute. So that's 5 parameters plus the commands, that's 6 items. And we're writing them from the write data tag in the PLC. And I think that's good. We're of course not doing automatic polling because you just send a command once, usually. And let's see, we have the data here, the write data. We need to set that. So let's do a move command. We'll do a 20 for a move command. And then let's move to a position of 17.2. We'll do a speed of 2, accel of 100, and decel of 100, and direction of 0. And we'll select all of those, apply those. So we have these values in the PLC. So now if I set the send command simple bit, actually that's here. So let's see the write data. Okay, we do have that in there. Send command simple bit, and I check that and apply it. So now that should go. Let's see if we look at the monitor. Okay, looks like that turned on. Let's see what happened in the RMC, in the event log. Okay, I got to pause here. We see that it did send this command. So we see right before it down here, 829, Modbus request received. Write multiple registers, address 401025, tells us a length, and then that became a command. So move absolute, we see that was 20, and then the same numbers we wrote 17.2 and so on. If we look at the axis tools, we should see the axis indeed did move to 17.2. So that's the process that we see. We do a write, it becomes a command, and the RMC processes it. So fairly simple to send a command. If we want to do other axes, we use the other addresses. We can send commands to multiple axes at once by writing to them in the same block. Now I want to talk a little bit about sending commands and doing the logic in the PLC. We have something called the command request acknowledge bit. Looks like I misspelled acknowledge. But let's say we're sending a command to the RMC to move the axis so the position goes from something to something else over time. So we send the command at this time, and then the PLC needs to wait for the in position bit to turn on so it knows the command completed, so it knows to go on. And so what the PLC does is after it sends this initial command, it does a bunch of checking of the in position status bit that is hopefully continually reading from the RMC. And when that in position status bit turns on, then it knows to proceed. There can be a little issue here with that. let's see this green line here. Let's say that's where the PLC sends the command to the RMC. And then the yellow line, let's say that's where it starts checking for the in-position status bit. Well, there's no guarantee that in the logic, when you look for the in-position status bit, that data you're looking at actually came from after you sent the command. It may have come from right before you send the command if the communications is not synchronized properly. So this is why we have a command request acknowledge bit. What it does is when you have a command and you're sending it to the RMC, you toggle the command request bit each time a command is sent. So from the PLC, when you send the command, we'll see how it works, but you toggle the command request bit. And then when the RMC is finished processing, it returns that same bit in the access status bits, bit 31. So you can see you set it to 0, and then you wait until the bit comes back as 0, and then you know that whole command cycle is done, and you're ready to actually look at that data, and you know that it's after the RMC processed that command. So when those bits match, logic can proceed. So first you set it to 0, send the command, wait for the 0 bit to come back. So the next time you send a command, you set that bit to 1, and then send it out and wait for it to come back and be 1, and you know the command is done. This really helps synchronize the command. It's happened sometimes that customers have problems with their PLC synchronization, and then we suggest to use this, and that fixes it. Using this is optional, it's not required. If you have your own method of synchronization and understand these issues, that's perfectly fine. You're free to do whatever you want there, but this is a method available to do that. It's a little bit complicated. It's a little bit goofy too, because back in the day in the RMC 100, when we had integers, we would actually set a bit in that word, like the highest bit, it would be the command request bit. But now we have floating point values, which work a lot differently. You can't just set a random bit in there and expect things to work. It becomes just crazy. So what we do is we kind of pretend to set bit 8 by adding the value 256 to the command when you send it. So the move absolute is 20. So if I want to set the request bit, I add 256. So it becomes 276 that I send to the RMC. And the RMC sees, oh, you set the bit, and when it has received the command and starts executing it, then it returns a high bit in bit 31 in the access status bits. So let's see how that works in practice. So we have a program here, right, with command request bit. Let me make sure that we have the other bits off here on the other programs so they don't interfere. So here we have a little bit more of a complicated user program. It's not that many rungs. We have one rung here, and then a second rung down here, and then another rung. So we're using kind of a state machine. We start with state 1. So state 1 is going to send a command to access 0 to move to a position value, and then wait for the access to reach in position. So when state becomes 1, we're going to wait for the send command bit to turn on. Then it's going to copy this data. So it's going to copy this 20, the move command, and then a position and velocity variable in the PLC, and then these values to this data array, and that data array is going to be sent with a Modbus write to the RMC. But here we toggle the command request bit, and then if the command request bit is 1, then we add 256. Of course, if it's 0, we don't add 256, and it's cleared. So this is how we add that command request bit. And you see each time it sends, we actually toggle that bit. Once we send the Modbus write, then what we do is while we're still in state 1 and we had set the send command bit, and we wait for this write here, we see that the internal tag is RMC write 2. We wait for that to complete. Then if the command request and status bit 32, that's the command acknowledge bit that came back. If those are equal, so if they're both on or if they're both off, that means that that whole cycle is complete and we got back the same bit, and now they're equal. So we know then we're done. Then we can start looking for the axis status in position bit. And the productivity software addresses arrays starting at 1, not 0. So this is actually bit 0 here in the RMC, the in position status bit that it's looking at. And then once it does that, then we move a value of 2 into the state, so we know we can go into the next state, and that next state just does something silly like increment, just because we want to do something to state. So it's basically just these two lines here. We add the 256 if the command request bit is to be set, and then we wait for the command acknowledge bit to come back and match, and we look at the in position and so on. So let's see how that works. The position variable is set to 12, velocity is 5. We can actually set those here because they're variables. Look at the right command here. So write data, that's going to be set by the program, so we don't need to change that. And let's see, the state is currently in state 1. So we should be ready to set the send command bit, and that will set everything in motion. So we set the send command bit, download that. And let's see, did anything happen? Not sure. Let's go look at the RMC and the event log. Well, I conveniently paused the event log, then I can't see if anything happened. Let's see if it moved. It moved to 12. So we had told it to move to 12 indeed. So looks like it must have worked. Oh, the state did change to 2 as well. So we see it went from 1 to 2, so must have completed. But let's go change it. We'll set the position to something else like 1.345, unusual numbers, so we actually know that happens. And we'll clear that, and we'll set the state back to 1. Okay, so let's see, I need to apply those individually, it looks like. Okay, so now if I set the send command bit, we should send a command that moves it to 1.345. So we have the send command bit. We will turn that on, and we see it move to 1.345. Now we should see here, it's taking kind of a long time to move there. We should see that, yeah, so these bits match. So it already came back, said it started executing the command, and now it's just waiting for the in position bit. Oh, there it turned to 1. So now it completed and then went to state 2. So that's the general method of using the command request and acknowledge bit. They can be a little bit complicated to program, but if you're having trouble with synchronization, we do recommend you try them. When you do communications with the RMC, when we command it to do things, we have a choice to send commands directly, just as we saw, or start user programs. Now, user programs can have a lot of motion logic and sequence in them, and it's designed specifically for sequences of motion, a little bit different than ladder logic. And so in many applications, it's really nice to use user programs because it's simpler and easier to program it. It responds at the loop time of the controller. You don't have to wait for a delay between the PLC and the RMC to tell it what to do next. So we generally suggest using user programs. But that said, there's situations where you may need to send commands directly. So when you do have this choice, you can use user programs or commands or both. Then you have a choice. If you start a user program, how do you know when it's complete? We had the command acknowledge request bit with the commands, and then you can look like the in position status bit. With the user program, you start it and you want to get some feedback. So we have 2 ways. You can read the task tags in the RMC, or you can create a variable that indicates done. So in the RMC, we can see that we have, let's see, if we look at the address maps, maybe indirect data map, we can browse to the tasks, task 0, and you can look at the status, and that status tells you whether it's running or not. I think you'd have to look at the help, see exactly what the bits are in there. You can also see what current program and step it's on. So you can actually stick that in the Indirect Data Map and read it from the PLC. I have an example here of a user program with moves. We see that we move to position 1, delay, move to position 2, and then move to position 3. And at the beginning, I have this variable. I set it to 0, and then at the end, I set it to 1. So the PLC can read that variable and be able to tell when it's set to 1, then that user program was complete. That variable is just in the variable table here. Let's see, I threw it right there, moves done, and you could read that, put it in the Indirect Data Map, read that from the PLC. So now I want to talk a little bit about Ethernet IP cyclic I/O communication. This is for frequently used data, not intended for large data blocks or infrequent communications. So typically your status, your commands, things that are going on all the time. If you want to read a big plot, then you'd want to use the explicit communications like we saw. Or if you want to write curve data, you would also want to use the explicit. So cyclic is for frequently used data and not large data blocks. The way it works, so we have PLC and RMC. We have the indirect data in the RMC that we're going to read from and write to. And we have the I/O data in the PLC. So in the RMC, we take the indirect data, send it to the produced data, send it to the PLC. And then for the PLC, we have its output data, and that gets sent to the RMC called consumed data, and that gets applied to the indirect data. This happens all the time at the requested packet interval, such as 20 milliseconds. You can change that. I think the RMC 200 goes down to 1 millisecond, 75, 150 goes to 2 milliseconds. So this happens all the time. You just set it up and bang, it's just magic, works. The RMC adds something on that called the sync register. So the sync register in the PLC will show up in it's just the first item in your array, so nothing more complicated than that. You can type in data in your array and send it to RMC. The first item, type in that, it's the sync register. The key here is that the sync register goes to the RMC, and the RMC sees it, and it pulls off everything else into the indirect data map, not the sync register, but it doesn't apply anything in the RMC until the RMC sees the sync value change. So the data is going all the time. The RMC just doesn't apply it till the sync value changes. And then once it does change, then it applies the data, and then it echoes that data out to the PLC. So this is just like the command request acknowledge bits. It's a good way for the PLC to synchronize communications. It also lets you take your merry time to build up your output buffer here, send it by just changing the sync out value, and then you wait for it to get back and you see it happens. The sync out is actually a floating point register and just needs to change, that's all. So we have an example here that I'm going to walk through right now of the Allen-Bradley PLC with the RMC. The RMC is at 0.0.75, and this is live. So let's see, we have the RMC first. We need to set it up. Not that one, it's a different RMC. Let me see. Okay, here we go. So first we need to set up the RMC75E CPU, make sure the Ethernet, looks like the IP address is correct here. And then Ethernet IP, we need to tell it to look at the correct area of the indirect data map. So let's go look at the indirect data map. Address maps, indirect data map. So we are going to map some areas. Looks like we already have some set here that the PLC is going to write to. It's going to write to start programs in the commands. And we'll add some information for it to write to here. Let's see what that was. So we will choose axis 0, status, target position, and actual position. And let's see, we'll do actual velocity and status bits. Let's see, let's get them over there and then duplicate that for axis 1. Okay, and we'll download that. So we want the PLC to read from item 0, and we'll do through 9, so that's 10 items, and then write to item 10 and through 19, so that's 10 items. So we'll go to the CPU Ethernet IP settings and tell it to start at 0 for the outgoing data. That's outgoing to PLC, and incoming from the PLC is going to be writing to 10. The length is actually going to be set up in the PLC. So click OK, download. That's all we need to do in the RMC. So now we go to the PLC, and here we need to add the RMC. So this is a Compact Logix, just a blank project at this point. We have right there, it has some built-in I/O, but no other modules. Before we start this, you do have to go to, let's see, Tools, EDS Hardware Installation Tool. But the Hardware Installation Tool likes to wait a long time. And so we're probably going to skip that. In fact, looks like it's making me wait right now. I shouldn't have clicked that. But this is the electronic data sheet file that we have. It's located on your hard drive in the same folder as the RMC tools is installed. So C:\program files, RMC tools. We'll cancel this because I've already done it. But you do need to install that EDS file first so the RMC knows when RMC, or so the PLC knows when RMC is. Once you've done that, we go to Ethernet. Let's see, I need to be offline to do this. So right-click Ethernet, new module. And I choose RMC, and this is RMC 75, create, and we'll call this my RMC, and the address of the RMC is going to be 192.168.0.75, and here we need to define the I/O. And let's see, reels, and we're going to do 10 reels plus the sync register, so I need 11. And we happen to have the same size in both directions. You don't have to have the same size in both directions. Electronic keying, usually a compatible module works, but yesterday for some reason I had to turn that off on this one. I don't know what the deal is, but normally you can have compatible. Click OK, apply that, and then we go to the connection. The RPI is 20 milliseconds, that's fine. And I don't need any other changes, click OK. Close that. So I see I have this RMC here. Now I can download this to the project. And click download. And now that's downloading it to the PLC, and the PLC will know about this RMC and will try to make a connection to it as soon as this is downloaded. And we should see when it's done, if we scroll down there, if there's no error, that means it has a connection. We can go into the RMC, look at, let's see, controller, view communication statistics, Ethernet IP, and let's see, that's the wrong project here. Let's go to that project, controller, communication statistics, Ethernet IP, and we see it has a current SIP I/O connection. So that connection was made, tells us which PLC it is, the IP address, tells what the requested packet interval is, and tells what the uptime is. So good useful information there. So we have made that connection. If I look in the event log, I should see that. It says SIP connection I/O opened, tells us what state the PLC is in. So that's good stuff there. We will also see that we have some controller tags for the input and output. So my RMCI is the input and my RMCO is the output. This is the raw input and output. So we're getting data from the RMC. Let's see if this corresponds to what we really have for data. So we have 0 is a sync register, but then it goes 20, 19, 20, 19, actual velocities kind of bounce around close to 0. Status bits looks kind of goofy. That's because this whole array thinks it's reals and it's not, but we'll fix that later. So we actually see it's working. And we can also see we have the output data, and the first one is sync register, and then the rest of it is actually sending data to the RMC when we want to send data. So let's see, we started at item 0, that start program. So 1, 2, 3, 4, 5. That's the command. So we should be able to send a command. If we start here, that's sync register, then it goes 1, 2, 3, 4, 5. So if I set this to 20 and then do maybe a position of 13.45, velocity, accel, decel. Now this data is being sent to the RMC. In fact, I should be able to see that data if I go set it up in the event log. So I go communications, Ethernet IO logging, I'll choose all, okay? And so it'll show every change. So if I change some of this, we'll go change 5 to 7, 100 to 20, and 100 to 25. It'll log every change there. Yep, so it changed to 7 and then 20 and 25. So good troubleshooting if you really want to see every change, but normally we don't want to see every change, so we'll go and turn that off. We just want to see requests, which is when we change the sync register. So we'll change the sync register now. I'll just set that to 1 and we'll see what happened. Request made, sync register was 1, sent 10 registers, this, and it became a command move to 13.45. So very successful. Now with this communications, you see this input and output array that you get by default are very just kind of mean, and you can't figure out what it says. There's no tags and so on. So we have a method whereby we can take the tags that you have in the RMC in the indirect data map here and port them directly into the PLC. Now I see in this one I have some tags already, but they were from a previous example, so I'm going to see if I can't delete those because they were previous, not here. So this is normally what it would look like when you add the RMC. We'll go download this. And so now we should be able to export our tags from the RMC and import them here very easily. So in the RMC, we go to 75EC CPU, Ethernet IP, and click this Export to Logic Designer button. And I need to tell it what the name is of the RMC in the Logic Designer. It's my RMC. Capitalization is important here, I believe. Next, and I need to tell it what data in the indirect data map I'm using. So 0 and 10, and I'm using 10 items each. That's correct. Click next. That tells me the PLC tags it's going to make for me, the input and the output. And of course, it makes all the underlying user-defined data types as well. And it's going to save that as this file. So that's going to be in my documents folder. Let me go change that to the desktop. Maybe that'll be a little bit simpler here. I'll save that, click next, and gives me some instructions there. Okay, so now in the PLC, I can import that. And the way I do it, and those instructions were given in that dialog I just looked at, go to the main routine, right-click a rung, and choose Import Rungs. So now I go to the desktop and I browse for that file, my RMCL5X, and it comes up with a dialog here for the import. And normally I can click OK. You can actually do this later and update it, and that's where this dialog becomes important. You can choose what items you want to update or not. Let's see, we'll go like this, import them all. And so now I want to show a little bit of what's happening here. When we imported it, remember we already had this mean looking input and output array. So now we're going to have a nice RMC in data user-defined data type tag and RMC out data with the nice labels and the right data types for every item according to what it pulls from the indirect data map, and 2 bits, an RMC send request bit and RMC send busy bit. And these automatically take care of the sync register for me. So if I want to send data, I put it in the out data, set the send request bit, and while it's sending and waiting for the sync in to come back, it will set the send busy bit. So any other requests in the PLC logic will have to wait while that's busy. So that's what it just imported for me, is these tags plus some ladder logic to take care of the sync register for me. So going back to look at that in here, we see rung 0 is very simple. It's just continuously copying that mean looking input array that's automatically coming in from the RMC. It's copying it into the nice looking my RMC in tag. And if we go to controller tags and look at my RMC in tag right there, we see that we actually have labels: axis 0 target position, actual velocity, and the axis status bits. Now we can expand those. We can actually see which bits are individually on, and we see that they have their individual labels. Makes it really nice to do your logic. And then the out array, that's just like we define the indirect data map. It has a start programs, and then the command, I can send a command if I want. So either way, trigger program or send a command. But that's the output data here that goes to the output once I set the send request and send busy. So for the output data, I fill in the data. Let's do a command. Let's do a move command to 1.477, and we'll do a speed. Let's see, accel and decels of just 20 and direction of 0. And so now to send that, I need to set the send busy bit. Or the send request bit. Where is that send request bit? Right there. So I set that to 1, and then it happened pretty quickly and got cleared, as soon as the whole transaction completed. The send busy bit was busy while it was happening, but it happened in just a few milliseconds, so we can't catch it here by eye. And if we go look at the RMC, the event log, we see that that became a command. So 1.477 and indeed sent the command. I can also trigger PLC, trigger user programs from the PLC. So I see here I have a program trigger set up so that if the start programs variable is not equal to 0, it will start these 2 user programs. If it's 0, it will stop them. So from a PLC, we should be able to set start programs to something like 1, as long as it's not 0, and I'll want to clear this other data so I don't also send that. And now I set the send request bit, set it to 1, and then it clears as soon as it's done, which is pretty quick. And let's see what happened in the event log. We had the user program running, so that means something must have started. I scrolled down here, and I see where task 0 started from a program trigger after the Ethernet IPIO request was made. And I can see in the task monitor up here that the user programs are running. Let's see, we can resume the event log. And so if I set the start programs to 0 and then set the send request bit, that should turn off the user programs. So sure enough, the user programs are stopped. So this is pretty much it for the basics of PLC communication. We've gone through explicit communication, cyclic I/O communication. There are certainly plenty of more details to be considered in the PLCs, especially for each individual PLC, but we cover those in the instructions that we have in our help and on the website. If you have any other questions about it, you can always contact Delta Technical Support and we'll help you. Kind of to summarize, some of the main decisions they have to consider when you're doing PLC is, do you want to send commands or start user programs? And of course, you can do both. If you send commands, you want to use a command request acknowledgement. If you start user programs, do you want to start them via a command so you can actually send the start task command, or via a trigger as I showed? And do you want to do cyclic I/O or explicit communications, or both? And if you do cyclic I/O, do you want to use a sync register? So these are some of the main decisions, and hopefully what we've gone through and explained will help you make these decisions. With that, don't have any more. Are there any questions? I'm looking in the question window. Looks like we don't have any specific questions so far, but go ahead and type some in if you like. Okay, well, looks like there aren't any questions. Of course, if you do, as usual, you can send us an email or give us a call. We'll be happy to help you. So with that, I thank you and hope you have a good time programming your PLCs with the RMC motion controllers. Thank you.
Thank you, Jacob. And thanks to everyone who attended today. We really appreciate you tuning in. Just a couple of quick reminders. Again, I mentioned at the top, recordings are available. So if you would like to, you can visit deltamotion.com. Right there on the front page, there is a link in the education section to past webinars. You can view recordings there. You can also see upcoming webinars. In fact, coming up in September, we'll have a webinar on RMC and HMI communications. Also, we have a forum. Maybe you are not familiar with our forum, but we have forum.deltamotion.com. There is a webinars topic there, and I post links to recordings there as well. Also, I don't know if you were aware, but Delta has a YouTube channel. There are actually a couple of YouTube channels with Delta related content. There's Delta Motion Control, and our recordings are available there. Also, Peter Nachtwey, our president, if you want to go in depth on mathematical analysis of control theory, this is a pretty in-depth topic, but Peter Ponders PID. So if you search for either of those channels, you'll be able to find that content. Thanks again for joining us. You'll receive a short survey. That's your opportunity to give us feedback. Our applications engineers take a close look at that when they're preparing these webinars. And so we would really appreciate it if you would like to complete that. I would appreciate that a lot. Thanks again. We hope you can join us next time.